Integral calculus. Today's video we're going to transition from differential calculus into integral calculus. And the idea of integral calculus is, think of the integral as kind of as the inverse of the derivative, and it's similar in concept to division being the inverse of multiplication. So usually with every process there's an inverse process, and you've learned, for example, that dy dx is equal to y prime of x. This is just our derivative, and the integration process just does this in reverse. We have the derivative and we have to figure out what it was that we differentiated. So this would be an inverse differentiation process. So probably the best way to, there's some guesswork involved in this. Probably the best way to get some idea of how we actually do this is just to do it. And one of the things that benefits integration, one's ability to do integration, is to know your differentiation techniques. The more you know about taking derivatives and what derivatives look like, the more likely it is that you're going to come up with the integral. And integrals are often referred to as antiderivatives. So we have a derivative that looks like 2ax. We want to know what that function was that was differentiated. Similar for 13 times x to the 12th, 2ax to the 2a minus 1, minus 8 fifths to the minus 13 fifths. What functions did we differentiate to get this? And the hint here is, in all cases, we're using the power rule. So let's take the first one. Yes, if you were thinking that's what it was, that's what it is. If we differentiate ax squared, we bring the power down in front, reduce the power by 1, we get 2ax. Okay, let's take a look at the next one. And you could pause this video and do these yourselves. Before we proceed along, we'll probably move through these pretty quickly, but we can see that if we have x to the 13th power, we take the derivative of y, we bring the power down, 13 times x to the 12th, reducing the power by 1. For the next one, bring the power down, we have our 2a here, reduce the power by 1, 2a minus 1. And lastly, perhaps a little bit more difficult, we have minus 8 fifths times x to the minus 13 fifths. Well, in a sense, a little bit more difficult. We can see that in order to get this coefficient here, this factor, we would take our exponent down, and there we have it. It's minus 8 fifths. So this is our exponent. And we reduce the exponent by 1. So we can see that if we differentiate this, we bring 8 fifths down, we reduce the exponent by 1, we get minus 13 fifths. Another way to write this is the way we originally presented this problem, as something to differentiate, and we found that it was going to be easy for us to apply our power rule differentiation by expressing it as x to some power rather than in this fifth root of 1 over x to the 8th. So I think, as you can see, you know how to do power rule differentiation. If you see functions like these, it's easy to figure out what their inverse derivative is or what their antiderivative is. But think about this for a minute. Did we miss something? The function y that we differentiated could have had an additional constant term. What would have happened to this? If we differentiate this, we have a constant c added in here. We have no way of knowing what c is, but when we differentiate y with respect to x, the derivative of c with respect to x goes to 0. So it disappears. We still get 2ax as our derivative, and the same for all these functions. Y equal x to the 13th plus c, y equal x to the 2a power plus c, y equal the 5th root of 1 over x to the 8th plus c. All these functions have the same derivative, except that we've added a constant in there, and there's no way for us to know what that constant is, unless we have some additional information in the problem. You may be working with a problem where you have some background information so you know what c is. So when we differentiate y is equal to ax squared plus c using the power and sum rules, as I've outlined here, just kind of go through the process, you can see that this derivative of c with respect to x goes to 0. We get 2ax again. So these constants, unless you have some additional information, you don't really know what they are. Okay, so here are a couple additional functions. Let's take a look at them. We know this one, we have a constant over here. We have 2ax plus b, so we know the derivative of ax squared will give us this term. We know the derivative of bx will give us this term. We know that the c will disappear. So this is just the standard formula for the quadratic. And we can see when we differentiate it, we retain information about two of the constants because they have the independent variable, as a factor. But c does not, disappears. The same for this function. We're just using the power rule in reverse. We increase the exponent by 1 to get n. We take the n back out. So we know that if we differentiate 2ax to the n, we get an n, a factor of n here. And we reduce the exponent by 1, we get n minus 1. But then we have to add some constant in there. So we have to keep that in mind when we're differentiating, when we're integrating. There's some information that we don't know. It's not, the result that we have is not exact. And the best that we can do is just say, okay, well, whatever it was that we used to, whatever it was that we differentiated to get this, which I'll just mention now, is called the integrand. This is the integral sign, and this is the typical way of writing an integral. This integral 2ax plus b with respect to dx. And again, we have this indefinite form with the constant c in there. So another term to introduce is that these integrals are indefinite integrals, and an indefinite integral is just a general solution that's valid for any value of x and c. So this value has to be determined through additional information that you might have associated with that problem. So they're non-unique. The c disappears when we differentiate. Just to make the points, when we differentiate this, we get start calling this the integrand, but c could take on any value, just to kind of emphasize the point. So our guest provides a partial answer. More information is needed. We don't know what c is, and what that translates to, when we look at these functions. If we have, here's a quadratic, and we've got a constant of c equal 200 here. We've got a constant c equals 0. Notice that these correspond to the intercepts. We don't know. There could be a whole family of curves here from y plus infinity to negative infinity, depending on what value we substitute for c. So this indefiniteness really means that we don't know which of these curves we're dealing with. This one, one in the middle, one up here, one down here. We don't know. So we have to have some other way of getting this information. Okay, I can tell you're getting good at this. The best way to get better at these things is just to give it another, to keep trying, to keep working through these puzzles. Again, we originally used the chain rule to come up with this derivative. The derivative that we have over here, we've got a minus sign that we bring down. We've got the minus sign over here. And reduce the exponent by 1, we get x squared plus 1 to the minus 2 power. Then we differentiate the inside terms to get the 2x. So we have minus 2x, x squared plus 1. Similarly, and I'd say pause the video and work through these. And confirm that the function that you differentiate to get this quantity would be a plus bx squared to the 3/2 power, and that this one would be 2x plus 1 squared. Now, in some cases, you'll get the starting function in a different format. We have here, we can see that the quadratic that we differentiate is going to be x squared plus 8x plus c. But the original function, if you remember back, we worked this problem, was x plus 3 times x plus 5. We used the product rule in order to differentiate this. And I think you can see here, if we carry out this multiplication, that c is going to be 15. So if we had this as our starting point, if we had some information about these two constants, we could figure out that c would be 15. How about this one? Well, if you estimate the inverse derivative of 2 over x plus 5 squared, we'll get that y is equal to minus 2 over x plus 5 plus our constant. However, the original function that we differentiated to get 2 over x plus 5 squared was x plus 3 over x plus 5. So can you see that in there? Most of us can't, not right away. If we compare those two functions, we have the x plus 3 over x plus 5. Looks like this. Notice that it blows up here at x equal minus 5. The denominator goes to 0. And the result for the inverse that we obtained in the previous slide is minus 2 over x plus 5 plus c. These are basically the same function, and just as with the two quadratics that we compared, they're just shifted versions of one another. So now, I've let c equal 1 in this case, and that's why it plots where it does. Notice that the derivatives, though, these are the two different functions, the original function and the function we came up with through that inverse process. They both have the same derivative. So we can't tell from the derivative whether the function that we differentiated is this one or whether it's this one. The derivatives are the same. Now there is, some equivalence between those two functions. We could figure it out if it was, important. What we can do is we can start with our y that we get. Let's say c is equal to 1. Then we let 1 equal to x plus 3 over x plus 3. We can do that. We can, it's still equal to 1, right? So we'll just let 1 equal x plus 3 over x plus 3. And I'd ask you just to kind of work through this process and go from this form, common denominator of x plus 5 times x plus 3, and distributing these terms in the numerator, and go through the algebra. And you'll find indeed that we can transform this result into this result. Okay, well, next time we'll talk a little bit more about indefinite and definite integrals. See you then.